So in this video we're going to look at one of the examples of simple harmonic motion you need to be familiar, and that's the mass spring system. The other example is the pendulum, and I'll address that in another video. Now if we set a mass oscillating and it's attached to one or maybe even two springs, we've already seen that it will oscillate with simple harmonic motion. If we plot the displacement time graph, we get a cosine function with maximum displacement here being the amplitude. So let's now analyse this a little bit further. If you've got an oscillating system like this spring with our mass on the end here, then the two things that are going to affect the period of that system are the mass, m, and the spring constant, k. How much stuff has to be moved backwards and forwards, and how strong a contracting and expanding force that spring has. So the mass and the spring constant affect the period. We already know from Hooke's law that the force that mass will experience with any extension from its equilibrium point will be k delta L, and we've seen already that for a mass spring system, for an oscillating system, the force is equal to minus a constant. For the spring, in this case it's k, times the displacement from the equilibrium position. But we can rearrange F equals ma to give us acceleration is equal to F over m, which is equal to minus kx over m. And we learnt in the last video that the acceleration of a system in SHM is equal to minus 2 pi f squared, with that being our SHM constant, times the displacement. So by analysing a is equal to minus 2 pi f squared x in terms of a is equal to minus kmx, then we can see that for a mass spring system, our SHM constant of minus 2 pi f squared is going to be equal to k over x. And as a result, you can work out what the spring constant is if given the relevant information. And the other thing to remember is an object is oscillating with simple harmonic motion if this here is its acceleration. This is the condition for simple harmonic motion. Now rearranging that previous equation means that we can work out that for the frequency, if we expand out the squared brackets, we get a frequency of 1 over 2 pi root k over m. So the period of oscillation for a mass spring system is equal to 2 pi root m over k, and that is our mass spring equation. So if you know the time period or the frequency, and so can work out the time period, and you know the mass of the object, for example, you can work out what k would be, and vice versa. The other thing that's worth noting is that if you were to plot a graph of t squared over 4 pi squared m over k, you would get a straight line.